Alrighty, hi everyone. Thank you all for coming. So yeah, this is our second to last workshop. We're going to be covering coordination and consistency, critical to maintaining any sort of distributed system. Um, so this week we don't have an event code because the board people didn't get it to us. He did? I thought that was an old one. Okay, well, 1 second. Let's see. Okay, lowercase cloud and then number 9 if you want it. Go right here. But apart from that, some of the topics we're going to be covering today are listed here. So we're going to start off with synchronization and coordination. Then we're going to talk about mutual exclusion and how that's handled with a distributed system. We're going to talk through some election algorithms and peer sampling, and then talk about data-centric and client-centric consistency. And then we're going to get to some consistency protocols that are used to implement those. And then finally, talk about replication management. So let's jump into it. So yeah, the first question here that I'm going to pose to you guys is, what is coordination? So I have kind of an image here on the right. Where's that? To kind of give you some hints of a scenario where coordination can be very important. But yeah, essentially, there are two types of coordination: data synchronization and process synchronization. So we can think of a scenario where somebody's kind of depositing money into their bank account. Obviously, if they deposit it at ATM A, we want another person to be able to withdraw that same amount from ATM B. So that process would involve data synchronization, because we need to make sure that internally both ATMs have the same view of the amount of money that's in the person's account. An example of process synchronization would be maybe if two processes that are running on the same ATM, so maybe two people are withdrawing and adding money on the same ATM, have a shared representation of the amount of money in that. Okay, cool. So yeah, and then another aspect that's very important to coordination is what's known as clock synchronization. So kind of getting a little bit more granular with that ATM example. Let's just say that we look at our watch and it says 150, and we deposit our money into an ATM. If this ATM has an internal representation of what the kind of global time is as 151, and a different ATM does not see that same time, depending on how we implement the synchronicity, we may not be able to withdraw that amount, or may not see that same amount in our ATM or in our separately. So kind of this poses the question of, like, how do we make sure that these have the same kind of view of global time, right? I'm going to get to that later today. Okay, but before we do, let's talk a little bit about what the difference between accuracy and precision is. So I have kind of a diagram here. It's a text. Does anyone want to take a stab at explaining what the difference between accuracy and precision is?
Accuracy is in the red spot, and precision is in the
Yeah, exactly. That's a good way of putting it. So from these diagrams, what we can see more or less aligns with what you just said. If we're very accurate, that means that there's very low kind of degree of variance in where we're hitting, but it may not be exactly what we want. Right. So, for example, this is target here. If we're very precise, that means that um, uh, we are closer to achieving our actual target, which is kind of like this goal here. Most of them are around the center, right? But there's kind of a good degree of variance. And then ideally, we have both high accuracy and high precision. So why am I bringing this up, right? Well, this kind of ties into the notion of internal synchronization and external synchronization. So, like I mentioned before, right, we have our own view of like, what the kind of global time is at each node in a distributed system. So our internal synchronization kind of corresponds to the precision. Like, are we actually kind of maintaining the state of whatever kind of data that we're working with in terms of the global clock that we have locally? And then external synchronization kind of corresponds to, okay, assuming like at that particular node everything is good, how does that fit into the larger picture of the distributed system? And how can we make sure that those nodes are actually coordinating together to be synchronous? Okay, so kind of now getting a little bit more into like the meat of how these things are done. Um, there's a very common protocol called network time protocol, where basically it's a way to kind of make sure that the global time is the same, or at least you're accounting for differences when you have two different nodes in a distributed system. So the way this works is that you have a client and a server. The client keeps track of its local time, and then it sends a request to the server. The server will keep track of its local time upon receiving the request and the local time when it sends the request, and then the client will receive the final request. So now the client has 4 timestamps, right? And they can use those to calculate what the network delay was, as well as what the kind of difference in the two local clocks would be, and then use that for future kind of communication with the server, and making sure that the two clocks stay roughly at the same point in time. So this is not going to achieve perfect synchronicity, obviously, right? But this is going to get us pretty close. So what if the clocks are not the same, right? How can we either repair that or handle it? Well, so we have two scenarios. One of them is if the client clock here is running behind the server clock. That's the easier scenario. Because what we can do then is use what's known as a forwarding clock, where we essentially just skip our clock forward to whatever clock cycle it needs to be at to match with the server. The trickier part is when our clock is ahead of the server, right? Why might that pose an issue? We could think of so I'm going to give you the answer. We could think of a scenario where maybe you've just kind of written something out to the database and it's dependent on the clock cycle for whatever reason, right? If we reverse our clock to kind of match with the server, then we're probably going to write that again. Or maybe we're pushing something out to a list, right? In that case, you're essentially be doing the same operation twice. And now our list would have 2 elements instead of just one. So to kind of account for that, generally we just kind of slow our current clock down, so to speak. So maybe we'll run like one cycle every 2 cycles on the like with the server time, to kind of let the server catch up. And then once the mall is comfortable, we'll kind of continue running. Does that make sense? Okay, cool. And then another algorithm that takes a slightly different approach is where we have a server that's pushing out, I guess, the kind of time updates to each of the clients. So in this case, we have a server here and then 2 clients. And this is this time like scenario A, B, and C. So initially, the clients obviously differ significantly, right, from the current time here. So it sends a request to get the view of the global time from the clients, and then the clients send back what the discrepancy between their view of the global time is and the actual global time that was sent in the initial request. So this one is behind by 10 minutes, and this one's ahead by 25 minutes. And then finally, the server will send the value to update for each of the clients. Okay, so this approach, oh yes, go ahead. Yeah, so that's just because like time moves forward. So yeah, it just happened to be 5 minutes ahead. So normally you would need to do that, I would think, but it's just for purposes of this example. Good question though. So yeah, what are some of the like strengths of this approach versus the other approach, and then and vice versa? Notice that this approach is doing something slightly differently. What is this? What's the difference between this approach and the other approach? The main difference. We just found it out.
Use the client instead of the server.
Yeah, you're getting at the right thing. Yeah. So here the server is actively pushing out to make sure that the clients are on track. Whereas with the previous approach, the clients are the ones that are sending out the requests, right, to make sure that they have the correct representation. So with this approach, you just want to be careful, right, because you have a single point of failure. So if the server for whatever reason breaks, then everything's just going to kind of get off track. Whereas with this approach, theoretically, you could just promote any node to the server, right? So if your server node dies, then you can just kind of use a different node and use that as the new global clock and keep sending requests there, and then kind of synchronize with that. Okay, cool. I'm gonna pass it off to Daniel now.
All right, so now we're going to talk about something called mutual exclusion. And so for in this example, we have the dying philosopher's problem. So the basis of the problem is that each of these 5 people, they can only eat their food if they have 2 forks, right? However, what's a sort of problem that could occur in trying to attain 1 fork? Well, let's say, each philosopher currently has their right fork, okay, and they're waiting on the left fork. Now, what do you think would happen here? Michael,
They wouldn't have all the forks, so they wouldn't be able to use the forks, they'd need 2 forks, right?
Exactly. So none of them are willing to give up their fork. So and they're all just waiting on the fork for the left philosopher to release, right? So in this case, it's gonna a situation is gonna occur which is called a deadlock. And so deadlocks occur when there's a cyclic dependency of resource acquisition. And so the 4 conditions for a deadlock is mutual exclusion, which means that only one process, or in this case, a philosopher, can access a resource at a single time. Holding and waiting, which means that you basically just hold on to a resource and you don't give it up until you finish what you're supposed to do. In this case, they're all waiting on a second fork, and no one's willing to release their first fork in order to break the cycle. No preemption, which means that no process can forcefully take away a resource from another process. And circular dependencies, which is self-explanatory. They're all it's a cyclic dependency waiting on each other's resources. And so ways to resolve this in a distributed system is with a token-based access to resource. So a token is basically just a piece of data that acts as a key that allows the process to modify a particular piece of data. And 2 concerns we have are deadlock and starvation, which means that for deadlock, as we said before, there's a circular dependency of resource acquisition. And then starvation means that, let's say, a process is trying to acquire a resource. However, there's other processes that are also trying to acquire that same resource. And our process in this case is a much lower priority. So each time it tries to get the access, other processes forcibly jump in, and they're high priority. So basically, our process never gets the resource that it needs, and so it's basically just stalled. And so there's 3 different types of distribution algorithms. So one is a centralized algorithm, which is basically like, let's say you just have a database, you can track up who has what token, and then every time you want to access a resource, you basically just send a message to the database, and then it gives you the token. But the downside of this is a single point of failure. A distributed algorithm is similar, except you have to put a consensus around who has a token. This increases complexity at the but you gain fault tolerance. And a token being algorithm means that basically a token just gets passed around each process one at a time, in a sort of round robin style. And then this is much more simpler to implement, and it also allows for fault tolerance as well. Since even if one of these fails, you can just remake the chain. And I believe the standard DB uses token ring architecture. I don't know this for mutual exclusion specifically, but this is quite common architecture. Okay, and then what you know.
Alrighty, so yeah, the main kind of scenario that we would need to use with an election algorithm is this one up here. So essentially, normally with a distributed system, we'll have a notion of like hierarchy among nodes, right? We'll have like either one master node or a series of master nodes, and then kind of a series of follower nodes. But if that master node dies or for whatever reason, like is having network trouble, we want our network to be resilient to that, right? And to be able to like recover and continue functioning. So generally, what we'll see is that we're going to just promote an existing node to be the new master node and try to recover in that way. And that's why we want to elect that node to be the new master node. Okay, so one common algorithm that you'll see is what's known as the bully algorithm. So the idea behind this is that once a node detects that the kind of old master is no longer functioning, then it will kind of start the election. So here, what's not shown is that 3 would have tried to make a request to node 6, and then it would have failed. in such a way that it would know that 6 is no longer able to kind of function. So then 3 would start an election, and what the way this algorithm works is that a node will look at its own kind of ID value, or whatever kind of identifier that it has, and we want to elect the node that has the highest like numerical ID value. So pretty simple. So this node will send an election request to all nodes that it knows that has a higher ID value, so 4 and 5. And then what those nodes will do is they will just acknowledge that request. And if they have a higher ID value, they will start a new election. So in this case, 4 received the message first. So it sent an OK, and it started a new election. 5 also received the message and sent an OK. But by that time, 4 already started an election, which is why 4 here is sending a request to 5 and trying to send a request to 6. The 6 is no longer in the network. And then here 5 will send an OK message to 4. And then finally 5 is, because there are no higher nodes in the network, it will probably try to send a message to 6 and see that it failed. And then it will send a new message broadcasted to all the nodes, notifying that it's the new message. So with this approach, one of the downsides is that every node needs to know every other node, or at least the nodes that have a higher ID value, right? So that can kind of be a downside because you have to either maintain a list of that. If you're adding new nodes and removing them, it can kind of be cumbersome. But yeah, this is a pretty basic one that's pretty standard. Okay, so another approach that Daniel kind of touched upon before, or at least referenced, is the ring election algorithm. So instead of passing a token around in a ring, we just kind of have set up our nodes in such a way that each node has adjacent to the next node. So what will happen is that here, for whatever reason, P3 knows that the previous mask, so P5, is no longer functioning. So it's initiating an election. And then it kind of forwards a request to the next node on the list. And then 4 will try to send a request to 5. It'll fail, so it'll forward it to the inexcusable 5 and go to 1, and kind of so on and so forth, until the message returns back to the initial node. And then the initial node here will know which node was before the failed one. So in this case, P4 will be the new master. So again, not too tricky to follow. But any questions on that one? Yeah, go ahead. Yeah. So this is yeah, go ahead. So you're saying 5 and 1 fail?
Yes.
Yeah, that's a good question. I think there there are a couple of different ways to handle it. It just depends on the implementation. More than likely, in some way, people will, assuming that it's built resiliently, will contact P2. Maybe there's another node or a series of nodes that are central that have like a list of all the other nodes or something like that. Yeah, it just depends on the implementation. But normally there'll be some sort of resilience built in for that. I think one of the trade-offs that you'll always see with any algorithm is that we can either store like as much information as we can, which limits the amount of like features that we have, right? And like the time it takes to do things, or we can go for speed, but at the expense of something. In this case, it'll be resilience, right? So if we choose to only store one node, like unlike the previous approach, right, we stored all the nodes, we would be faster here, right? We don't have to store as much space, but the trade-off is that it would. So good question though. Okay. So then another algorithm that was introduced in the textbook that we were reading to kind of provide context for this, that it's not really as set in stone, but it's I guess it's loosely referred to as like a wireless election algorithm. The reasoning is that when you have a wireless system, the connections will not be as stable, meaning or not as reliable, I should say. So we want to have a good way to maximize, I guess, the network reliability. So the way this algorithm works is that we have our kind of initial node here that detects the failure, which broadcasts the election, and it will do it to all adjacent nodes. And then the next node will kind of do the same, and it will propagate through the entire network. And then the N, you'll notice that all these nodes have like numbers on them, right? But they also have letters. So the letters here represent the actual node like IDs, and the numbers represent the capacity to kind of it could be either the reliability or the capacity to send out like, multiple requests, some sort of metric that we're using to keep track of like how well a node would do if it was a master node. So what we do after we send out the request to every node is that the request will feed back through the network their own capacity or the capacity of one of the nodes that they reached out to that was higher than their own. So in this case, the column is 2, it'll feedback here, but the 3 is higher, right? So it'll feedback 3. But this node here, B, down here, somewhere in the network, there was a node with 8. So it would have received 8, and then it would feed the 8 back up to the initial. And then finally, we can just kind of feed this, the notion of the new node, which in this case will be H, back through the entire network. One more time. So yeah, the intuition here is that this is supposed to be very resilient for adding new nodes. But if we add a node here, for example, that's connected to these 2 nodes, and then the master node dies, right? We can it doesn't depend on a fixed network kind of topology. That makes sense? Okay, and then I think this is the last one we're going to cover, but this is a cluster-based architecture. So the idea is that we just kind of send out a election request to the adjacent nodes. Yeah, I think this one is well, I haven't seen it as common, but basically the idea is to do what's known as an epidemic algorithm, where by sending a request to adjacent nodes, they can there's some sort of metric that each node will have that'll just like with the previous algorithm that will keep track of whether a node is good or not to be the master node. And then we will do some sort of aggregate metric at each node. So this is like maxing and averaging it. And then by doing so, each node will perform a computation, and we'll be able to know whether it's a better choice or if neighbors are a better choice. I don't have it on the slide here. Honestly, I do not remember off the top of my head how it aggregates the final results. Do you know that? Okay. Yeah, let's not worry too much about this one. It's not as common, but if you're interested, look up epidemic algorithm. Because that's what that means. Okay, sorry about that. Pass it off to Daniel.
So now we're gonna talk about how to keep data consistent across all your replications. And so we have something called a data store, which all it means is that if you have a cluster of databases working together to provide fast, reliable, access to the client nodes, you can do this a few use cases. So distributed shared memory, something like Redis, we basically use it as kind of a distributed like RAM, essentially, a distributed database. That's like Cassandra or one of those like DB type things, a distributed file system. And these are 3 ways to keep track of how far away that your actual data is from the your consensus state, like what's the sort of like drift or variance of your database replications. So one way is numerical deviation. You actually look at the differences in the values stored across replications. Deviation and staleness, which basically means like, what's the oldest replication that has not been updated, and deviation order of updates, which means that if you have a sequence of operations, what's the sort of difference between what the operations should be ordered in and what they actually are. And so one consistency model is called continuous consistency. And this is when we actually create a guarantee that our values stored across our replications will not vary by a certain amount. So let's say you're running like a stock exchange, right? And you have like 100 databases. we could say in our use contract that says, if a client does these things, they will have, every time they read from our database, they'll have, an updated value of the stock price that's not going to be different from the actual stock price by more than, let's say, 2 cents, right? And then we also have sequential consistency, which means that in order of operations stays consistent. So let's say you change a value to 3, then you change the value to 4. All the replications should show that value of 4 and not the value of 3, and that's basically all that means. And causal consistency means that if an event affects another event, then the order of operations stays the same. So this is very similar to sequential consistency, except for the fact that you don't really have a global clock idea, right? Causal is really just like, if you have like a single process, the events from that single process are processed in order, but there's no guarantee in the case that processes are concurrent. So let's say you have a process A and process B. So this is sequential concurrency. We see that as like a sort of global, or actually, no, this is causal consistency. So normally, our Y should process first in sequential consistency. However, the only guarantee we provide is that process 1, Rx and Wx are processed in the order. And then P2 events are processed in order, but they can be like interlaced among each other. Right. And then another goal is that data is always coherent, so it always adheres to the contract that we provide. And it's often implemented with critical sections. So if you take CS 33, that's the Ryman's thing, or you open MP, that's the way to do it.
Cool, yeah. So data center consistency seems to be pretty good, right? So why would we need to have any other notion of consistency? Well, with data center consistency, we add quite a bit of additional overhead, right? Because we need to make sure that like for every write that we do, the data is consistent to any read that's happening anywhere, right? So that's not always a requirement. So for example, you can think of a web page, right? That maybe somebody is editing a web page and wants to add like a new line of text to it. We don't necessarily need that to be immediately available globally, right, to all users. So long as eventually it propagates through, we should be okay. So that kind of lends us to the notion of client-centric consistency, where the main goal is that we're ensuring that if I'm a client and I access something, and I make an edit, and then I access it again, it'll be consistent with my initial edit. And we'll get to that in a second, like what the specific kind of tenets are. But a common example would be, so let's just say we have some large network there, and then we have a bunch of replicas of our kind of database. So if we kind of on a laptop access or whatever content that we want, so maybe it's a website stored in this database, and then make an edit, save it, and then kind of travel across the country, and then open up the website. Although we may be contacting a different replica there, underlying content should still be the same. Hence, kind of client-centric consistency. For that same client, it should be consistent. So, what we'll see with this model is that these are the 4 requirements. So quickly going through them, we need monotonic reads. So that means that all subsequent reads, like I mentioned before, by like a single client should use the most recent version of the file, which should include the client's latest update. Or if somebody updated it and the client's latest update was overwritten, then they can include that. This is more recent. It should include monotonic writes, meaning that the order of the writes by the client is enforced. So if I make a change, right, travel somewhere, make another change, then travel back, I should get both changes, not just one. They should be in the correct order. And there's this notion of read your writes, where on the client side, any writes that I make should be reflected. So again, getting back to that same example, right? If I make a change and then travel somewhere, I need to be able to see the writes that I just saved to the file when I'm reading that file. And then finally, writes follow reads. So this is if I do a write after a read, then the updated version of the data will be at least as new as the red blue. This one's a little tricky. But yeah, does that make sense, everyone? This whole. Okay. Cool.
Alright, so we talked about the consistency, and now we're gonna go over protocols that are actually used to implement this. So there's a class of protocols called primary based protocols, and what this means is you basically just select one replication and set that as your primary. This basically controls all your writes, and so for a primary backup protocol, we basically just have writes. Writes are forwarded to the primary, and then they're propagated across all the replications. And then for reads, since it doesn't actually affect the state of the data, they can be accessed from any of the replications. So in this picture here, this is a primary based protocol or primary backup protocol. Now, what do you guys think is happening over here? Right, it's ordered from W1, 2, 3, 4. So let's just go over step by step. So for W1, its client is sending a message to its own local replication. So what do you think this message is, Michael?
It's a write.
Yes, it's all it is just a write request. It is sending it to its local replication. Now for step 2, it's sending from its local replication to the primary server. So why do you think it would have to send a message to the primary server from its local?
It has to read it.
Exactly. So the primary server needs to know that a write is happening since it's going to control all the writes. Now for step 3, right, it's sending it to its to all the backup servers, right? Now this happens because it's basically just propagating these changes and updating all its backups in the data store, right? And for W4, right, why do you think that's happening? Simon? Exactly. That's exactly right. So, things get lost in the network all the time. Like, you see packet drops. That's what's good. That's what could happen. So you basically just need a way to confirm that your writes have successfully taken place, without any issues. So that's W4. Now, we also have the R1 and R2, which is basically the messages exchanged during reads. Now, it's only 2, so I'm sure you probably can guess what it is. It's just like they send a request and then acknowledge it, right? This is contacting a backup database because reads do not affect the entire data store, right? So your local will be just fine. Now, for a local write protocol, basically what happens is that you can write to your local database. However, there's also this propagation step where you have to explicitly propagate all your changes you made locally across the entire replication. And so I'm not going to go over this too much in detail, but yeah, it's very similar to this one. The only real change is that whenever you want to propagate a change, whenever you want to propagate your local changes, basically what will happen is that you would have your local database, and that basically says to the current primary that I'm going to be primary for a little bit, so let me propagate these changes, and it basically does the same thing as the primary backup, right? And so what would be the advantages of using one over the other? Have any ideas? Brian? Tap it out. Okay. So yeah, basically it's like primary. You only have one primary server. And so this is very inefficient in order to actually write. So this is only really good for in use cases where you're doing very few writes but a lot of reads. So for example, a CDN, if you know what that is, Cloudflare provides a service as where you have like a web server and a bunch of replication across the globe, fast access, and you basically just set one of the web servers as your like master node. And then every time you want to update your website, you just tell the master node to propagate those changes in a similar way to this across all the replications. Now, for local write protocol, the advantages of this is that we can basically just do a bunch of writes on our local servers, and only propagate them when we actually need to. For example, if you're accessing a wireless application, right, you could just have a local replication, and then once you're, once you lose connection with your mobile device, like propagate any changes that you make. This used a lot in like edge computing. Yeah, if you ever heard of that. Yeah, so this is pretty much used if you're doing a lot of writes and not so many reads.
Okay.
Now, here's an example of a replicated write protocol. So as we saw before, we had like a primary and a backup. Now, there's another way to do this where we don't actually have a single point of failure. Like if our primary database comes offline, we're kind of screwed. So one way is to have a couple active replications, and we just basically have all the servers vote on which version to accept. And so basically, in order to read, we have a read quorum, and then what this means is that you basically just have them, to make sure that there's no read-write conflicts. So if a write's currently taking place, there's not going to be any, inconsistency in our data. And then the writes also must assemble a write quorum. And then the two rules are that if you want to write, that you basically have to have majority of all the replications, and then the total number of read and write quorum members have to be greater than the total number of replications. So this might be a little confusing. It's like, how do you have more servers than the current number of servers? Well, each replication can have more than one role. So all this means is that you have to have at least one replication that's a reader and a writer.
Okay.
Okay.
So now that we've talked a little bit about replicas, let's talk specifically how we actually make sure that the data, like what data we're transferring between each of the nodes to make sure that the replicated data is consistent. So yeah, the first kind of type of replica that you'll see is what's known as a permanent replica. So this is something that's pretty foundational for any database system. So for example, if we're trying to do a bunch of reads globally, so for example, with like a CDN that Kafka, again, I was mentioning, we probably don't want to have just one database, right, that everybody is reading from, whether you're in China or Britain or whatever, right? It's not going to be super efficient. So what we can do is establish permanent replicas, which will, like, we're going to go there, set it up, with the intention of it staying there, right? So generally these will be read only, but theoretically they could be of any of the forms that Daniel talked about. And we will have our primary database that will push out whatever changes we have to the replicas, and then people can use them. The next type here is what's known as the server-initiated replica. So generally, these are dynamically allocated by some sort of server, either the master node or some sort of compute associated with it. And these will be to help with performance, and then they'll be deallocated once demand dies down. So yeah, like similar use case to permanent replicas, but normally more expensive, right, because you're dynamically allocating them, but also temporary, right? So you're not paying for them full. And then finally, we can have what's known as a client-initiated replica. So this is more akin to the notion of a cache. So for example, if I'm doing a lot of reads to like 10 websites, right? Maybe my browser will cache the website so that I don't even have to go out and talk to any of the like the owned replicas, I guess, by whoever owns the domain, right? I can just kind of cache it. Does that make sense? The distinctions there? Okay, cool. And now getting a little bit into like how we maintain the replicas. So the first thing here is let's just say we make a change to one of our nodes, right? Maybe it's the primary database. We need to send that change out to the other nodes, right? To notify them like, hey, you need to update your data. And there are a couple ways to do that. So one way is through what's known as active replication. So this is where if let's just say I write a SQL query to add 10 rows to a table. Instead of updating the data here and then sending the data, we're just going to send the request to all the replicas, and the replicas will run the same request itself. And then in doing so, each node would have effectively made the same change. Another way would be to kind of just update the data here at the primary node and then send the updated data over. so that the other nodes can update their local version of the data. And then kind of going hand in hand with this is what's known as an invalidation protocol. So let's just say, kind of going back to that example of the website, our data does not need to be, it can be stale, a little bit stale, right? Maybe we don't need to update all the replicas immediately. What we can do is just send an invalidation, like a notification to all the replicas saying, hey, there's a newer version available. So that they know, but we can kind of save time and cost or whatever, to avoid sending all the new data right now. And then when the replica is ready, you can kind of request it and then get the update. Okay, cool. And then this kind of ties into the notion of a pull-based versus push-based way of making sure that the data is consistent. So what we'll see here is that there's this notion of a lease, which is effectively when the primary node tells all the secondary nodes, or each of them, I guess, hey, up until this point, I will keep you informed of what the new data is. And then once that ends, the lease is over, and then the secondary node has to renew the lease actively, like requesting to the master node, okay, renew the lease, and then keep telling me what the latest version is. So the reason, or a couple of reasons why this could be useful. Maybe we have that stale data scenario, right? So the replicas don't have to be up to date all the time. Maybe we have those like replicas entering and exiting. So we don't want to kind of constantly be sending out data if we don't really need to. And then there are different types of leases there. So we can have a lease based off of the age of the nodes, one that's based off of the renewal frequency, and then kind of the state of the nodes, if we have some sort of way to share the state of each of the databases or replicas. And then finally, we have a notion of a unicast versus multicast versus a broadcast. So this is a little diagram that shows up. It says unicast, which means you're sending data or sending the request to a single node. Multicast is a series of target nodes, and then a broadcast is sending it to all of those. So yeah, there are different reasons why you may want to go with one or the other of these approaches. Maybe this node is very busy, right? The master node, not too surprising. So you'd want to send it to a single node and then have this kind of contact disappears, that kind of thing. It really just depends on the way that we choose to implement it. Considering whatever the main cost that we're going to be with. Okay, any questions on maintaining replicas? Cool, then I think that's all that we have for our slides. Okay, you wrote a little bit small. The code is on the board though, so feel free to do that if you care about the ACM points. But we will be turning it over to project time now. So anything else? Okay, we will have food next week, so and we'll probably have more than enough. So if you know people that want pizza, they can come and grab some. So, but yeah, apart from that, for the projects, if you are stuck or like don't know what to do, definitely ask Daniel and I. There's a series of templates that you can work off of, and then look back at the project spec doc that has the deliverables there, which are things that you can work on.